Arterial calcification, the deposition of calcium in blood vessel walls, was long understood as an inevitable consequence of aging, the biological equivalent of pipes becoming encrusted over decades of use. The research on vitamin K2 has fundamentally revised that understanding, revealing that vascular calcification is not a passive, structural process, but an actively regulated biological event that can be influenced by nutritional status. At the center of this regulation is a K2, dependent protein that prevents calcium from accumulating in arterial tissue, and autophagy appears to be part of the mechanism through which K2 keeps this protection operational. Matrix GLA protein, or MGP, is produced by vascular smooth muscle cells and is one of the most potent inhibitors of vascular calcification identified in biological research. But MGP requires carboxylation to function, a post-translational modification that depends entirely on vitamin K2. When K2 is insufficient, MGP remains in an undercarboxylated, inactive form and cannot prevent calcium from depositing in arterial walls. Large population studies, including the Rotterdam study, found that individuals in the highest tertile of vitamin K2 intake had significantly lower rates of aortic calcification and cardiovascular mortality compared to those with the lowest intake. Differences that were not observed with vitamin K1, which does not activate MGP at meaningful levels. The autophagy connection operates through K2's role in vascular smooth muscle cell maintenance. Autophagy in these cells serves the same quality control function it serves elsewhere, identifying and degrading damaged mitochondria, misfolded proteins, and cellular debris that accumulates with aging and chronic stress. Vitamin K2 appears to support this autophagic surveillance by activating downstream signaling pathways in vascular cells. And studies examining K2's effects on arterial calcification in cultured cells have found that autophagy activation is part of the mechanism by which K2 removes calcium deposits and reduces smooth muscle cell transdifferentiation into calcifying cells. The vascular protection, in other words, is partly a cellular housekeeping story. The dietary sources of K2 divide into two forms with different kinetics. Negative for Malawian quachas, found in egg yolks from pasture-raised chickens, butter, and organ meats, has a short half-life in circulation and requires frequent dietary intake to maintain tissue levels. -7 Malawian quachas, found predominantly in natto and to a lesser degree in aged hard cheeses, has a much longer half-life, providing stable circulating levels from less frequent consumption. Natto's K2 content of approximately 850 micrograms per 3-ounce serving is so high relative to other food sources that it sits in a category by itself. Hard cheeses aged for over a year provide around 75 micrograms per ounce, meaningful and accessible for those who find natto's distinctive sticky texture and strong flavor an obstacle. The critical warning for anyone on warfarin or other vitamin K antagonist anticoagulants is essential here. Increasing K2 intake can affect anticoagulation stability and requires coordination with the prescribing physician. This is not a reason to avoid K2, but it is a reason that changes to K2 intake should be made predictably and communicated to the clinical team managing anticoagulation therapy. Cardiovascular benefits from consistent K2 intake appear to develop over 3 to 6 months of regular consumption. This is a long-game intervention, not an acute one.